Okay, this video is to continue my work. Today's date is the 19th of March 2026. The time now is 2:40 p.m. So this is basically on the magnetic memory model, and I formulated in a way that you have a system of accumulation and commutation, via system model. But model is basically the first model I have for the system. And one by that is a memory system, memory model system. So, first of all, you have linear probing, which is the indexing of a hash table to index something, index some kind of artifact. If until to solve collisions. Linear probing solves collisions. The collision table is really the bit in the memory where the memory is stored. This is really the magnetic memory addresses up. Basically, you get electromagnetic waves, and magnetic memory model. It's not resolving collision; it just stores stuff. You have to resolve collision fast up. You got a linear problem, and you got quadratic problem. Now, quadratic problem is a magnetic memory principle where magnetic memory is used to probe multiple bijections of nodes via electromagnetic spectrum. So the magnetic memory model is magnetic memory is based on electromagnetism, which is the principles of magnetism via electro systems. Shares of the state machine via the electricity machine. One of the formulations, I'll continue to ensure the bijection is correct. But for me, correct project means you're probing over an area space. You have a system of here. So you have 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8, which are the 8-qubit binary systems. You have the opposite. So you have one half, one half. Should be. You have the opposite of the system. Or so get this represents A-bit addressing, 8-bit addressing over hexadecimal pairs. What this means, you have one eight system, the byte system over eighth, and you have the equality. You can have A8. You're gonna have A to A B C. You have A to H, via hexadecimal A0 to A0 A0 to A0 to A8, or 00 to H8. No, 01 to H8, which represents the system of an architectural platform, such as a processor. I'm trying to formalize this mathematically via the magnetic memory system, such that you can define a quadratic probing system where a block of 4 times 4 via addressing and inverse addressing things you hold, such as 1 over the system, a system over its own weight, maintain coherence over the model. For example, you have an address here, A1 to A4, A1 to A4, A1 to A4, which is just a range here. A1 to A4. This range of A01 or 01 to 04 is interest the same as indexing A1 to A4 via hexadecimal pairs. A1 to A4, but via an electric system, because the address is homogeneous. So you have 2 states of indexing systems. So A, B, C, D, E, F, G, H. Because the H maps onto the value of the system. So if you want to index this system here, this column here, I can define this as span And this span will be B um, uh, B. So I'm defining B to B6, and B2 is another span which that can use competition. This memory can be put in parallel. B2 to F6. F6 is a column vector in computer space. It's a column vector because the region is has used homogeneous. So you have rows. You can get vector quantities in a system like this binary system like this. The ultimate goal of this system is to ensure that the memory model has some coherence among it, and you can use it to perform quadratic probing over a set of data. So the system can be flashed. It's called a flash or filter sequence. The goal of flash is actually a filter is retrieving or sorting. A filter is sorting, searching, merging, and retrieving. Ultimately, the goal of filtering is retrieving. But these are operations that are called functors. They map neatly with one another. There's no all function, all functors, and that's a flash sequence. The magnetic memory model over a block set of bytes over addressing, like houses in these addresses, are not just linear, they can be quadratic, they can span. And you can use all the houses to determine a solution space, where the solution lies on the web, or the search space of a system. These two can be computed over vector properties, dot product, cross product, based on 3D computation of cosine. You can do the dot product, you can do cross product. For example, I can, if I have any information in these cells, I can accumulate values over the cell period. Based on what was studied there. This written memory cell, by the way. This memory cell that stores bytes of data. For example, these are addresses that store bytes of data, and the bytes of data are a state machine. Okay, let electron state be defined by E equals S, where S is a discrete state, E is digital inputs, gamma is a digital transition function, and S0 is a start symbol of the machine. And like the magnitude 1 be, omega is continuous waveform, psi is the analog waveform, U is the waveform evolution operator. Basically, it's equivalent to digital transition function. And W0 is the waveform initial start step. The reality lies is that there's a bijection between D and S, D and S, which is basically omega, which is over a continuous waveform. D is basically a state, and D is a bijection such that S is a state that implies omega. The omega is the waveform of the states. So this means that there's a state machine that's mapping the two states that are isomorphic before this is called the bijection D. It's a disjoint bijection. It's a disjoint union of the state. D such that gamma, which is the transition, SA equals U DS theta, where theta is a maybe state. This is an analog waveform. Theta is a maybe state of a system. This means that every digital transaction has a waveform evolution that carries same information. Yeah. Every digital waveform has a waveform evolution that carries the same information. So mathematically, to compute over this, there will be a set state, one over basically If I was given 24 frames per second of an image of a system, and the 60 frames in a second, 60 frames in a second would mean 60 frames per second is an FPS target, and you get 60 frames per second in a moving image, in a static image. 60 frames in a non-blurry static image. 60 frames per second. You have the search space of the addressing via the architecture, which is basically 4 times 4, which is 16 bytes of memory computer. But the no difference because using the 16 bytes, 64 times 4 bytes of data, which would be exactly or precisely. This is there are 2 bit processor for 64-bit processor. A 32-bit processor can handle a model of 4 gigabytes of RAM, which is 2 to the power of 32 bytes of data at one time. But the 64-bit processor is can theoretically address up to 16 extra bytes of RAM, but only uses 4 gigabytes of RAM. So, a stereo can usually 4 gigabytes of RAM at any one time for any one operation in parallel. The parallel is time or space. If you're opting for time and space, respectively. A single bit processor can use 64 bytes of data to the power of 64 bytes of data, which is basically 16 extra bytes of RAM. 16 bytes of RAM. 16 RAM, 16 gigabytes of RAM, gigabytes extra gigabytes of RAM. Gigabytes of RAM. So when you talk about gigabytes and megabytes, you're talking about the gigabytes of RAM. This is the gigabytes of RAM. But the 16 extra RAM, bytes of RAM is 16 plus is 20. So you get 16 extra bytes of RAM used because it grows quadratically. This is what my theory holds because it goes quadratically. So you're gonna go 4 times 4 is 16. 16 times 4 is whatever 16 times 4 is, which is 16 times 4, which is 64. So this shows that because of the growth curve, this processor aligns with the model of theoretically for video editing, 3D rendering, and large database applications. These are large database applications. Computationally, it's in essence you get like a span, which spans regions of memory, and you got a span, you got a range, which is the range of memory. You have a span 2, can span a row, it can span a column. And span a row can mean you skip 2 or 2 or 1, 2, 1, 2, span 2, you skip 2 rows. For example, basically, you have a span of a row, which is this row here. But if you're actually 7, you can span space row, span 2, space, span 2 from 0, 0, and you get a start from here 2 to, you can then enter the address of the memory you want to accumulate. This is what the Rift ecosystem, Rift Lang, does. It uses Rift out to determine how the system works by doing but using an electrical model system, electrical system. Moreover, you have 60 millimeters per second, and that is 60 millimeters per second is 1 second. And you have in a 64-bit architecture, you have how many bits of RAM? That's to the power of 64, which is basically 2.64 bytes of RAM, which is basically 16 gigabytes of RAM. Exactly 16 gigabytes of RAM. Let me show you 2 power 16, which is basically oh, this is wrong. 65. Yeah. This is like 16 gigabytes of RAM. Yeah, but you have the span on the previous system, which is 6,500 and 5,500, 500,000, 536, 536. 0.0. My point is that you can separate this process in parallel via a GCD operation. For example, you have the conjugate model of the binary systems, which is 1/2, 1/4, 1/4, 1/6, and 1/8, 1/10, and 1/12. You have a span 1/2, which is listen, in 1/2 stage you have a number like 1, 0, 1, 1, 0, 1. 1/2 of a 0. These are all conjugate model of some. Usually, this number here, 1. This is moving backwards because it's a binary system. Because of 1, 0, 1, 1. So 1/2 of, and then a sixth, and then an eighth, and then a system represents half of 2, half of 2, half of 2, 4, 6, 8, 10, and 12. And that will be half of 2 will be half 1 divided by 2 is 0.5 plus 1 divided by 6 is 0.7 plus 1 divided by 8 is 0.8 plus 1 divided by 12 is 1, 0.9. Now, 0.9 is literally the number, this is 0.9. But this can be used for operation. So don't need to go to operation. Now, apply this to a matrix. A matrix has a row and a column. And the row or column represents the row index and the column index. So this is a model of the space of system. So, for example, it takes 24 frames per second. 24 frames of a second is equal to 6 times 4, 24. 6 times 4. Now, this one can be processed as 4 units of time. 4 units of time, which would be 4 units of time would be 6 times 4, 2 times 3. Can be processed of units of 4, 2, and 3 are the local maximum. Because the maximum is 6 and 4. Basically, at the local maximum, at one time, this can be when the system is storing and loading, storing and running, storing and running, not loading, storing and executing code. So the system can bidirectionally process something at runtime based on the half model. So the conjugate system. So for example, you have half of 4. This 4 represents half of 4 bytes of 4 time units, time slices. Half of 4 bytes. Half of 4 at the minimum. So half of 4 bytes will be so if you have calculator, if you have 4, if you have half of 4, you have half of 4, which is basically 4 divided by 2. If you have half of 4, it's 4. If you have half of 2, 4 divided, you have 3/3 or improbable fractions in the model, but the model is computing via a left shift of the byte space. So you allocate memory via a row and align via a row and another to a span, and that's where memory comes involved. So the memory computation aligns them, basically computes the dot product of the system. And by computing the dot product, the system enables you to accumulate systems of do the row conjugate model. Basically, I love to do the conjugate matrices. So if I have a matrix that I want to store, if I have 24 seconds of a frame, 24 seconds of a frame is 60 times 24, 60 frames per second. 60 times 24, I have 1,440 frames per second. 1,440 frames per second. I can process per second. If I disjoint chess in two, if I disjoint chess in half, if I complete the GCD of this, The frames are stored are and each frame takes how many frames does each frame? Each frame takes 1 second, and you have each frame stores is the storage capacity of this frame is 1,440 memory to flash to store. It will just be saving, so that'll be the exclusive operation. And the goal is to have two vectors. So you have the crop product. To basically the dot product, which you have to do a triangle of a vector to store it in the system and use a left vector. So let me try and compute it myself. So you have 60 times 4. Yes, you have the matrix model here. So you have the rotation. So you have to rotate the matrix some of the system because the rotation have basically you got north rotation, which is disjunction, north south rotation, which for the matrix, north south rotation, north and south poles. We have a rotation of 45 degrees, and the rotation determines the computation. So you're gonna have the rotation be part of the magnetic poles. You're gonna have north and north repel, which means you are having a disjunction, a bijunctional disjunction, and you have bijunctional attraction. Usually, incubation, the victim model applies here. I can't do it because I'm holding this pen. I'm holding this all up, but it's too much for me to process here. So you have 1/2. So every in a matrix here, in a say matrix a matrix of 10 2. This is a column matrix. This matrix has a north and south pole, and this has a north and south pole. No, wait, it doesn't have no. It doesn't. This has a row conjugate. 2 and 10. Row equals 1. So C equals row, and the measure 10 to is 2. So if you have a system, this structure, it computes in parallel by showing that the 10 2 and 2 to 10 are row conjugate. We have a half. You have the measure stuff for half. So every half determines the segment of memory you accumulate per time. So you get a half of the matrix, a half of the system. A quarter is 6, 8, is 16. You can have 3/2, but you can complete half and 4/4 minus 1 over 4 minus 1, 1/4 minus 1/3 minus 1, 1 unit of the system. But that will be due to pipe equals pipe double left shift, to the matrix itself. And that will give you the two operations that matter are exo and pipe left shift for alignment via row and column, and pipe right shift, which is why right shift, which is basically the 3-arrow right, or to the size of the data you want to accumulate. So pipe left shift will give you the number. Pipe right shift will give you the size of the data or the memory data you operate on based on the data structure model you're using or the memory segment you're using. I can't demonstrate that here because I've got things to do, but that's the whole idea. If you can compute it yourself, go ahead. But just remember to use the GCD LCM to decipher to compute the lowest common thing can compute over can get over the quadrant proof. Namdi.